Good. So far we have seen like what is a power electronic converter actually. So we have not discussed anything related to how it is realized, but what it is doing, the basic principle of operation for the DC-DC converter. That's what we have seen. And we have seen how the passive elements like inductor or capacitor, these things are used to filter out the harmonics and then make the characteristic of the load or source different. So either making it voltage stiff or making it current stiff. So these kind of things we have seen. And the flow of power, whether it is happening in single stage or it is happening in multiple stage, these kind of things we have reviewed. And what we have come up, that we can have the voltage buck operation from this converter. If we are trying to feed a load with a lower voltage than what is available, Vg, then this is one configuration which can give us the desired result. So L and C are appropriately modeled. So L will basically be modeled on basis of how much peak to peak current ripple you want to have, and C will basically be designed on basis of how much peak to peak voltage you want to have. So these are the parameters which define what value of L or C we are going to have. Of course, the value of load with other parameters also defines whether it is continuous operation or discontinuous operation. So all these things we will discuss in much more detail when we have any dedicated power electronics course. So because this is dedicated for machine drives, so I am focusing on the drives part more here. So that's why I'm only touching these, how these converters are realized and what things are happening, and not going into detail of how the current ripple or voltage ripple or all these things will look like, and how to make it continuous or discontinuous operation. And then some more advanced converters, let us say synchronized buck, synchronized boost, and then some isolated converters. So these kind of things we are not discussing over here. That is not part of the curriculum. So in the power electronics course, definitely we will discuss all this. Now, coming to the topic. So today we are going to realize this switch, what we have called in general as single pole double throw switch. Having 3 terminals like this, and this we are going to realize on basis of what? On basis of the current and voltage conditions. Now the first question which comes to our mind when we start designing these things is, what is a switch? What do you mean by a switch? So from our experience or from our other examples, we know that switch is a bistable entity and it has certain qualities. Let us say it can block some amount of voltage and it can conduct some amount of current. These are the properties which it has. So typically when we say like it is blocking the voltage in one of the stable states, that is called off state. And in the conduction, that we call as on state, the another stable state. So these two states are stable, which means you have to change, you need to give some triggering, some gate pulse or some other condition you need to change from switching to switch from one state to another state. Let's say on to off or off to on. So you need to change some parameters, whether within the circuit or through a gating signal or something. Now, first we understand what properties an ideal switch should have. What is an ideal switch? Ideal switch is something which has, let us say, in the blocking state, it can block any amount of voltage, ideally. And that blocking is in both the directions. Let us say it can block in this direction or it can block in this direction. And during this blocking state, this I leakage, if at all, is there, this is very close to zero or actually equal to zero. So there is no current conducting during the off state. And it can block any amount of voltage, whatever is desired. Now, in the on state, it can conduct any amount of current, and there is no voltage drop when it is conducting. Let's say in that on state, the voltage drop across the switch is zero and it is conducting any amount of current. And this conduction can happen actually in both the directions. So it has bidirectional voltage blocking capability and it has bidirectional current conduction capability. Now another important property which it has, that if we want to make transition from one state to another state, that can be done with minimal effort or zero effort. All these are ideal characteristics, which means it does not need any energy, practically speaking, to change from one state to another state. So of course this is ideal and this is stable in both these states also. So this is what the properties which we expect in an ideal switch. Now when it has zero current conduction in the blocking state and zero voltage drop in the conduction state, of course the power loss in the switch is zero in both the states. This is another important property of any ideal switch. So what we try to do, we try to meet these characteristics as much as possible. Of course, we cannot meet all the things given over here for the ideal switch, but to whatever extent we can match these properties, that we will try to have. Now, let us see some practical devices which are there in the domain of power electronics or in the industry which are being used. So first switching device which I always say is our diode. This is of course uncontrolled switch. So symbolically we represent diode like this, and we know that it blocks any voltage which is in the reverse direction and it conducts any current which is in the forward direction. So it has reverse voltage blocking and forward current conduction. This is the property of diode. Now, if let us say we draw the IV characteristic of diode, how it would look like. So ideally, it should be like this. which means conducting any positive current and blocking any reverse voltage. So this is what the ideal characteristic of diode is. But of course, we know the practical diodes have some limitations. So the characteristic deviates from the ideal characteristic slightly. So it goes like this. Of course, it is very close to the y-axis. It is little bit exaggerated over here. And then on the reverse side, there is a breakdown voltage. So it can hold up to this. The rated voltage is given as V blocking rated. So this is the breakdown voltage, beyond which if you apply any reverse voltage, the diode will break down. And the forward direction, it will conduct the current, but there will be certain drop across the diode while conducting. And what the characteristic suggests that there is a slope. So which means if we have to draw the equivalent circuit of this diode in the off state and on state, what we can draw in the off state, it would look like, okay, let me draw it separately. So here, which means it is an open circuit with very minimal of leakage current, and it can block the voltage in this direction. So which means the power loss across the device will be V blocking into I leakage. So for all practical applications, this I leakage is very small, close to some microamps or something like that. So this is practically we can take this loss as zero. Now during the conduction, as I said, there is certain drop. So if you observe in the characteristic, it is starting little late and then it is having a slope. So this indicates that there are two elements which are there when it is conducting. One thing, it has a resistance which is giving the slope, IR kind of characteristic, and it has a forward voltage drop, which is this small component which is seen on the x-axis. So this can be written as VD, which is almost, let's say, 0.7, 0.8 volts, and for power diodes it is a little more. The RD could be valued depending again on what is the design parameter for the diode and all. So it could be few milliohms. So then if we have current conduction, of course, the other side. So we can write the power loss in the diode like this. So this cannot be ignored, of course, because the VD and RDS quantities are finite. So this is how we can compute, if let us say any current I is flowing through the diode, then what is the power loss in the diode. So two things we have observed, that it is a single quadrant switch. With this characteristic, and it has conduction loss given by or dictated by these parameters. Now the next device what we can see is a control device which we can call as BJT, bipolar junction transistor. This is a controlled switch, and to be more specific, it is a current controlled switch. So symbolically, it is represented like this. So collector, emitter and base terminals are shown over here. And dependent upon this I base, the device goes into either saturation mode or cutoff mode. So we are not operating the device in the active zone. This we need to understand. We are not operating the device in linear zone. So either it is in saturation zone or it is in cutoff zone. So here, what characteristic it has? It has capability to block any voltage which is in the forward direction, and it can conduct any current which is again flowing in the forward direction. So this has forward voltage blocking, and it has forward current conduction. Now, ideally, if we plot the characteristic of this device, how it will look like, the IV characteristic. Again, because both the quantities are in the forward direction, so I would be on the positive side and V would also be on the positive side. So it operates on the y-axis when it is in on state and operates on the x-axis when it is in the off state. Now this is ideal characteristic. If we try to see how the actual characteristic look like, again you see closely that there will be some drop and then it will have a more sharper rise. And then something which is very close to the x-axis. So what we call these two zones. So one is this. This is very close to y-axis. I am drawing it in a little exaggerated manner for visibility. So this is called the saturation zone, or it is the on state. So it is conducting some amount of current and then it has some drop over here, having slightly tilted characteristic over here. And the other part is this, which is called the cutoff state or the off state. So these things are dependent on the base current. So depending on what base current we are driving at, this will go into these zones. Now, if we see what are the equivalent circuits for this device in different zones. So this is also a single quadrant switch. And in the cutoff zone, first of all, that is easier to do. It is like an open circuit. With minimal amount of leakage current and this voltage blocking VCE. So the power loss for all practical purposes, VCE into I leakage, this can be regarded as 0. Whereas if we go for on state, what we will see that there is some drop. That's what we are able to see over here. So which means primarily the device in saturation state depicts a voltage drop in the forward conduction direction. So if this is IC, there is some voltage VCE sat that is there in the conduction state. And because this tilt is not very, no, it's very sharp rise, so we may ignore the resistance component, but sometimes we may consider depending on what data sheet is saying. So in this case, again, if we are ignoring the resistance, we have the power loss IC into VC sat. So which means the power loss is proportional to the conduction current. And this VC sat value is close to, let's say, 2 volt or 1 volt, something like that, again depending on the design of the power BJT. So this is the BJT, the another switch what we will use in our circuits. Now another very famous device which is there in most of the polyphonic converters, that is the MOSFET. So we know that this is also a controlled switch, and this is a voltage controlled device. So symbolically we have this device, an NPN, sorry, the N channel MOSFET, and by default these MOSFETs come with body diode. There is a body diode by default present on the MOSFET. So it has terminals, drain, source and gate, and through this gate voltage relative to the source, the device operates in various modes or various zones. Now here the device again has forward blocking capability and forward current conduction capability. These are the characteristics. Now because we have the body diode also available over here, so it gives another addition in the current conduction. So we may have bidirectional current conduction with the practical diode, with the practical MOSFET. So having the anti-parallel diode. So because of this anti-parallel diode, what we get is bidirectional current conduction. FET alone, the MOSFET alone has this property, forward voltage blocking and forward current conduction. But because of the anti-parallel diode available, naturally it has bidirectional current carrying capability. Now again, if we see the characteristic, which is very similar to BJT but slightly different also. So the differences we will observe very closely what is there, and that will define how this can be used in circuit or where it can be used in circuit. So the ideal characteristic, so here we are having IV. Ideal characteristic is again forward current conduction and forward voltage blocking. This is only for FET. I am ignoring the diode in this. So this is the characteristic for the FET. Again, it is single quadrant switch. But if you go for the practical or the actual characteristic, it is different. So here it is originating from the 0. The BJT was starting little late, but here it is originating from 0. It has much more slope compared to, or let us say the slope is much more evident in case of FET compared to BJT. BJT was almost perpendicular. Here it is little more visible. So something like this, and then something very close to the cutoff state. So again, like BJT, we have zones of operation. This is some called as saturation zone, and the other one is called as cutoff zone. So of course the saturation zone is where the device is on, and cutoff zone where the device is off. Now this characteristic tells very important thing about the MOSFET. When we draw the equivalent circuit, the off state equivalent circuit for all the devices are very close. It is very close to the open circuit. With the V blocking, there could be some leakage which is very small, few microamps. So for all the practical applications, P loss is very close to zero during the off state. So this is like an open circuit in the off state. That is what we have seen. Now, if we come to on state, what we observe from the characteristic that there is starting, or it is beginning from zero, and then there is a slope which is not very sharp, which is not very steep. So which means the dominant component over here in the on state equivalent circuit is a resistance, what is called as RDS on. So whenever the device is on, it is equivalent to a resistance, and depending on the current flowing, there would be power loss in the device. So RDS on is typically like 0.8 ohm or 1 ohm, or maybe even lower for some of the modern FETs. Now they are having resistances in, let's say, few tens of milliohms, and it could be even lower depending on the technology. So the power loss, if we see in the diode, is so this is the thing what is there. Now another very common device which we use in our converters, and this would probably be the last device maybe which we will discuss in this course. So just for the sake of completeness, we'll quickly see the IGBT, insulated gate bipolar transistor. So here, this is also a controlled switch, and the symbol for this device is well known, similar to BJT in the power side and very similar to MOSFET on the gating side. So we have gate instead of base, what we have seen in the BJT, and we have collector and emitter. So this is very similar to MOSFET from the gate side. So this is also driven by voltage VG, and it is very similar to BJT in the power side, which means the conduction and blocking properties. So this will also block a positive or forward voltage, and it will allow a forward current. So what happens that the BJT properties will be very much visible in the IGBT characteristic if we try to draw the IV characteristic. So it is very similar. I will quickly draw for the sake of completeness. And then we have slightly late start but a very steep curve, and then so again we have two states, the saturation, this is little exaggerated, and the cutoff. So the device goes into on state in this zone and goes into off state in this zone. Very similar to BJT. Now that's what we have been calling it. So then on and off state equivalent circuits are also very similar. So in off state it is like open circuit, very much open circuit, and in on state it is like a voltage drop, which is like VCE SAT. So for BJT, which is VCE SAT is close to 2 volts, and Depending on what current is flowing through this, the power loss will be IC into VC sat. Good. So this is the thing. Now, based on these properties, what can we say about the uses of these devices? Uses means when we have to use, let us say, several devices in parallel, which are easier to connect in parallel, which are difficult to connect in parallel. So of course, because MOSFET depicts a resistance, so it is very easy to connect MOSFETs or operate MOSFETs in parallel. So if there is mismatch in the resistance of RDS on 1, RDS on 2, the current through the MOSFETs would be balanced accordingly. Let us say the I current is flowing through the complete circuit, then I1 and I2 would be distributed according to what is RDS on 1 and RDS on 2. And this will balance out. So there is no runaway. It will always balance out each other. Whereas it is very difficult to operate two IGBTs or two BJTs in parallel because of the voltage characteristic. If let us say one is turning on first, then there will be more current flowing through this and there will be more losses associated with that, which may further keep on dragging the device towards that end. And that's why this paralleling is very, very difficult. Now, the next thing, which device to use where? Let us say we always compare. We have MOSFET and we have IGBT. So which one to use? Let's say we have a power level given for the circuit, or let's say current level given for the circuit, which device to use, whether the MOSFET or the BJT. So how to decide that, BJT or the IGBT, you can say. So then if let us say we plot the power loss, what is happening in the devices with respect to the current flowing through the devices, we know that the IGBT is like VC sat. So the power loss is proportional to the current flowing. Whereas here, this is like a resistance. So the power loss is proportional to I square. This is very important difference because the IGBT will see a kind of linear characteristic. The slope will be dependent on VC, of course. So let's say like this. And the FET will be something like a quadratic curve. So it will go like this. So what we can see for the lower ranges of current, we have FET better than IGBT because it has lower power loss. Whereas as we go beyond a certain current level, we have IGBT better than the MOSFET because of lower power loss. Now the power loss in FET overtakes the IGBT. So that is why IGBTs are very much advantageous for the high power applications, whereas FETs are very good for low power applications. Now this discrimination is up to the person who is designing the converter, that which to call as high power, which to call as low power. So typically few hundreds of watts, that is the FET limit. And if you starts going into the kilowatt or few kilowatt region, that is where the IGBT should be used. So we have seen good amount of now explanation about all these devices and what their characteristics are. But now coming to the important point, how do we realize the desired converters using these devices? So first thing, let us say all these devices we have seen have single quadrant operation. If we ignore the anti-parallel diode in the MOSFET, so most of the devices or all the devices are like a single quadrant device. So diode has certain characteristic: forward voltage blocking, forward current conduction, reverse voltage blocking, and all other devices forward voltage blocking and forward current conduction. So if, let us say, someone asks us that we have to realize a switch which has a characteristic which is like multi-quadrant, let us say it has bidirectional current conduction and unidirectional voltage blocking. So what do we do? One example we have seen, a MOSFET with anti-parallel diode. This will have the voltage blocking in only this direction, whereas it can conduct current in the positive direction, that is in the forward direction, or in the reverse direction through the diode. So this is one example of having the multi-quadrant operation. The other thing could be, if you have any IGBT, just put a anti-parallel diode with that. So this will also give operation like the multi-quadrant switch. Now, similarly, if we have any other requirement as well, let us say we want to have bidirectional voltage blocking and unidirectional current conduction. We may have such requirement depending on the circuit. So what would be a good example for this, or how this can be realized? So we all know that any device has forward blocking capability and forward current conduction capability. And if we attach an anti-series diode, now I am calling this anti-series because it is somewhat similar to anti-parallel. So let's say an IGBT which has the blocking capability like this and conduction capability like this, it is connected or cascaded with the diode which has blocking capability in this direction and conduction in this direction. So altogether we are getting conduction in one direction but blocking in both the directions. Now both the polarities can be blocked using this kind of arrangement. So this is one example. We can have many more where we can realize these kind of switches. Now, there is one switch available in nature which is like inherently multi-quadrant property, having this kind of property, which is thyristor. So thyristor inherently has both the blocking capabilities, the positive and negative, the reverse and forward blocking capabilities, and it can conduct in one direction. So this IGBT with anti-series diode is very much equivalent to a thyristor. Of course, the switching characteristics would be different. This is only the stable IV characteristics which I am talking about. So with this, now we are ready to realize our converters. The realization of buck boost and buck boost converter, what we have seen. So systematically we will see what are the requirements for those, and then we will realize that. Now the first converter, let us say if we take, that is our buck converter. If we go step by step, it is very easy to say what will fit where. First, let us draw the circuit. Now, these are the terminals P, T1 and T2. And then, let us draw the two states. First one where P is connected to T1. This is where P is connected to T1. Now we see what are the voltage and current polarities in this situation. So we have current flowing in this direction and we have the blocking in this direction for PT2. So P is at the VG terminal whereas T2 is at ground. So the polarity of voltage which is getting blocked through PT2 is like this. So in the other configuration, when P is connected to T2, we have PT1 open. So the important property that the current in inductor cannot change its direction immediately. It has to slow down, go to zero, and then only it can reverse. So it will continue to flow in this direction, and that is why through PT2 the current would be in this direction. And for PT1 the blocking will be in this direction. So if let us say we take that current is always forward conduction, then what characteristic we are expecting for PT1 and PT2 that can be drawn very easily. Let's say this is for PT1 and this is for PT2. So I will draw only the ideal characteristics are enough to define the quantities. Now let's say take P1. So it has this forward conduction and then it has forward blocking because current direction was also like this. So that's why I call it forward blocking. So then it comes here. Now for PT2, the current is again forward, but the voltage is like reverse to what current is. So from minus to plus, that's why it is having a reverse blocking capability. So we can very easily tell which device can fit here. For PT1, we can have any of the active devices, let's say BJT or even MOSFET or our IGBT. So any of the devices will fit for PT1, any active device. And for PT2, we know very clearly that it is only diode which can match this characteristic or which will match this characteristic. So now our SPDT switch, this pole T1 and T2, this can be realized in this manner. So let's say I take BJT. So this is our pole which is always connected to the inductor and then either it connects to throw 1 or it connects to throw 2. So these are the devices which are in place to have the realization of SPDT switch. Now we can say that our buck converter is realized completely with these power electronic devices. So this is how we have seen the famous buck converter circuit. So these are the steps through which this is realized. Similar exercise we can repeat for the boost converter and then the buck boost can be taken as an exercise for you people to complete that. So let us quickly see what are the requirements for a boost converter. So let's say we are trying to realize boost converter. It has inductor, connected to the input voltage source and then we have the load connected across a capacitor. So of course the terminal connected to the inductor is always pole. Let's say I call the bottom as T1 and the top as T2 because first the inductor has to charge. It has to maintain that current and then it can pump something to the load. So which is why T1 is drawn here. Now the two states, if we draw first one, when P is connected to T1, it is like this. And T2 is open. So our capacitor is feeding the load in that time. And then we have the other mode when the charged inductor is now feeding our load. And PT1 is open. Now quickly we can draw the polarities of the current and voltages. So of course the current in the inductor is in this direction, and because this is connected to ground, P is connected to ground, we have this polarity coming over here. Now here we have in the off state or in the other state what we have is because now conductor, the current through the inductor cannot change abruptly, so it will continue to flow in this direction. So this will see current in this direction, and the device now, because this is connected to the output voltage, so it has this polarity plus minus. So I hope you are following. Now if we draw the IV characteristics, the ideal IV characteristics of PT1 and PT2, what we will see. So always the current I say is in forward conduction mode. So that is always positive, and we decide V on basis of the current direction. So let's say current is flowing. So this is from positive to negative for PT1. So this is a forward blocking requirement along with the forward current. And for the diode, the current polarity is here, but the voltage blocking is opposite. So that's why it comes here for PT2, sorry. So this is our PT1 and this is our PT2. And yes, of course, we know through our experiences also, and we can clearly see that what devices fit over here. So let's say I take BJT over here, or any active device can come over here for PT1, and diode can come over here for the PT2. So we are able to realize this boost converter in this manner. So if I draw that for sake of completeness, what we will have, so this is how the power converters are realized based on what characteristic we want for a particular switch. So this will be very much important when we are going for AC motor control and all. There these things will be even more utilized for realization of converter, whether it is voltage source or current source. So these concepts will be very much important. So that is how we are realizing our boost converter. So the buck boost converter can be taken as an exercise, and you can try on your own. Buck boost, or I call it flyback. This converter can be taken as an exercise. You try on your own and just see whether you are able to put those devices in place or not. We already know through our textbooks that what device should be there. So just see that if you are getting that result in this manner or not. Good. So with this, we have completed all three aspects of our DC motor drive. We have analyzed the load characteristics. We have done the controller design. We have done the power converter design. So all three aspects we have completed for the DC-DC converter and DC-DC converter fed motor drive. So those who joined late for this course, they may watch the previous lectures. It is uploaded in the files section. And if you have any doubts, we always meet on Tuesday for lab. So that time we can discuss all those doubts. So all three aspects are now complete for the DC motor drive. And particularly we have taken the case of DC motor with separately excited field. So this completes this portion, and next we will start the control of induction motor. So some amount of discussion on the open loop drive, and then further we will move towards the closed loop control. Which involves your vector control or even slip compensation or any other thing. So that's all for today's class. Any doubts, if you have, you may ask now.